Okay, so now we're up to section 4.3, and we're going to talk about Riemann. So it's Riemann. It's a German name, so you pronounce the second vowel there. Riemann sums. Okay, and also this idea of a definite integral. Okay, now we talked about antiderivatives and indefinite integrals. We aren't going to quite, get to the truly amazing thing that took many good mathematicians years to actually figure out, but not in this section, but in the next, in 4.4. But let's start with these Riemann sums, and really the idea is, as we think about that notion of finding area, so if I wanted to find the area under this curve f of x, when we were doing it in 4.2, we had all the same width delta x. But, in the end, there's actually no reason, you can prove it, we're not going to go through the proof, but there's no reason why each of these rectangles has to be the same width, as long as you make sure in the limit they all go to 0. I can't leave one of them really wide and have all the rest go to 0. I need to have them all go to 0. So what we have for a Riemann sum is, we're going to have our x0, x1, x2, all the way up to some xn. And, on our interval, this is A, that's B. And so we'll define what we call a partition or a mesh. Okay, a partition or mesh on AB. And all that requires is that A is equal to our x0, but then that's strictly less than x1, strictly less than x2, strictly less all the way up, strictly less than xn minus 1, strictly less than xn, which happens to be b. So it's just, instead of having to be equally spaced, we're going to allow them to be all over in there. And so then our delta xi is equal to the width of the ith interval, first, second, up to nth. So that is x sub I minus 1 is that width. Okay, so that's our delta xi. And then if we let ci, so x I minus 1 is less than or equal to c sub I is less than or equal to x sub I. If we let that be any value in there, then our Riemann sum is just a summation, the sum I equals 1 to n of our function f at ci times that delta xi. So all that's changed from the previous section is now we can pick this. It doesn't have to be the midpoint. It doesn't have to be the left-hand side. It doesn't have to be the right-hand side. It's any point in there. Now, typically, you're going to either pick the left, right, or middle, or something like that. And then our delta xi, our width of each rectangle, doesn't have to be the same. But this then, This is a Riemann sum. Oops, spelled it wrong. This is a Riemann sum. Okay, so it's much like our stuff before, but that's all it is. Now, this is not actually have to be an area. You don't have to think of it as an area, although it's very, very helpful. But really all we're doing is we are adding up a bunch of values of a function, each multiplied by a delta xi. And now if we say that the norm of delta, our partition, is the maximum delta xi, then what we do, if we were to take a limit as delta x goes to 0, well, what we're actually going to do then is, as n goes to infinity, we're going to make sure that then our largest interval, okay, our norm, then that will be going to 0. Okay, again, we can't leave one really big or something like that. All of them have to go to 0. Okay, so that is a Riemann sum, and that's all it is. And so we'll stop there with this one.